I was watching this series of videos by the creator Sebastian Legg, where he makes an AI that plays chess from scratch. The videos were super cool, and after watching them I thought, I want to do that. The only problem is that he is smart, and I am not. So I wanted to try something similar, but easier than chess. That's when I remembered a game that I've played a few times in my life called Othello. Othello is a 2-player game that you might have never heard of before. However, the rules are very simple. Players play on an 8x8 board using these black and white pieces called discs. Whenever a player places a disc on an empty space, they look at each direction surrounding that disc, and they can flip any discs of the opponent's color if they are sandwiched. Both players play back and forth until either all discs are one color or the board is completely full. Then, the player with the most discs of their own color wins. Othello is perfect for my plan since it has a similar structure to chess, but the gameplay possibilities are much easier to work with. I began by making the game itself. The board was pretty easy to create using Godot's UI tools. Then, I used my overflowing skill with vector art to make some disc sprites using 2 differently colored circles. I chucked these into an animated sprite 2D, and now we have pieces that can flip their color. I also added a few quality of life features. There's a yellow highlight that shows the spot where the mouse is hovering, and there's also a blue highlight that shows where the player's valid moves are. For the game logic, we mostly just have to be able to tell if a given move is a valid move. Then we need to be able to flip the nearby discs after the turn is made. In order to detect if a given line is flippable, we need to see 1 or more discs of the opposing color, followed by a disc of our own color. If we see a blank space, or we don't see any opposite color discs, then we won't be able to flip anything in this direction. Along with our disc flipping logic, I also added this fun little click sound when you place a disc. It increases the pitch with each flip, so you can make some satisfying combos. This is all that's needed in order to code Othello, but playing with my imaginary friends is starting to get boring, so let's get started on making the AI. However, I won't be making the AI in Godot. Godot isn't very fast, and we need this AI to be as fast as possible, so instead, I'm going to write the AI using C++. This will be a separate program, and it'll pass the moves it chooses to Godot through a server. This has an additional benefit where the AI will run on my local machine, regardless of who's playing against the AI. So that way, someone can't just play against the AI on their iPhone 2 and wonder why it's not playing very well. But Thomas, I hear you ask, since you chose C++ for your backend, that must mean you're pretty good at it, right? If you were making a board game like Othello in your Intro to Programming class, you would probably use something like this to store the state of the game. This is an approach that's mostly based on object-oriented design. This is perfectly sufficient in the majority of cases, but we're trying to be fast. So instead of doing this, we're going to be storing the board using something called bitboards. The idea behind a bitboard is to use a large binary number to store information about the game. Here's a chessboard. It has 64 cells total. If we have a 64-bit number, that's 1 bit for each cell. So here's a bitboard that represents whether each cell on this chessboard is occupied or empty. However, it can't tell you which piece is at each spot or even what color it is. The solution? Now, with 2 64-bit numbers, we can represent 2 pieces of information about each cell. We could represent the black pieces and the white pieces, we could represent the pawns and the non-pawns, and so on. So how many of these bitboards do we need to represent a board of Othello? Well, if we just use 1, then we could have the 0s represent the black discs and the 1s represent the white discs. But unfortunately, we wouldn't be able to tell if a cell is empty. So we need 2 bitboards, one of them to tell if a cell is empty or not, and the other will tell us if a cell is black or white. Bitboards aren't just small, but they're fast. You can use bitwise operations to combine or modify them extremely quickly, especially in C++. The biggest downside to this is it can make the code extremely hard to read. Here's what it takes to set a given cell to a certain color. If you're used to using bitwise operations, then this probably doesn't look too bad, but it can be annoying when your entire codebase is filled with stuff like this. We're almost done with the setup. All we need now is to connect our C++ server to our Godot client and ensure that we can pass data back and forth between them. I thought that hosting a server in C++ would be easy. Just do like server.start or something, I don't know. Evidently, I've spent too much time using high-level languages recently, because that is not how C++ operates at all. Sockets are a mess, and I don't even want to attempt to explain the stuff you have to do just to get them working. So let's skip ahead and figure out how I dealt with this roadblock. Setting up the TCP client in Godot wasn't nearly as bad. It still had some oddities, but everything was much better documented. Anyway, after all this work, I can finally play against an opponent who picks their moves completely at random. The algorithm that we'll be using for our AI is called Minimax. Basically, we want to iterate through every possible move that both players could make up to a certain amount of moves into the future. Then we want to evaluate the boards that result after these moves by certain criteria. Using this evaluation, we assume that both players will be playing as best as humanly possible. Of course, human players are usually not going to play ideally, so that allows the AI to gain ground. This is of course assuming that the evaluation function actually indicates the correct value of boards, which we'll get into later. If you want to understand Minimax better, I highly recommend this video by Sebastian Legg. He explains it much better than I can. He also explains a technique called alpha-beta pruning, which I implemented but can't be bothered to explain. So here's what our Minimax looks like. If our depth is greater than our maximum depth, then we evaluate the current board position. Otherwise, we get all the possible moves from this position and loop through all of them. For each of these moves, we're going to apply this new move to the board and then recurse on our Minimax function. We then keep track of the best evaluation score of all these possible moves and pick the best one. Minimax is great, but its efficacy entirely depends on this evaluation function. If it lies and says that a position is good when it actually isn't, then Minimax won't be very effective. So how can we tell if a position is good? Well, the first thing we can do is get the current score and evaluate that. This is certainly better than picking random moves, but it leaves a lot to be desired. Even though score is what determines the winner in Othello, chasing after it will leave you vulnerable in the endgame. It's not uncommon to have a player up by a lot of points all game, and then get destroyed in the last few turns because the opponent was focusing more on position and waiting for their moment to strike. So while we do want to evaluate a position based on score, we want to focus more on other things in the early game, and then only focus on score in the endgame. The more moves we're able to make, the better. We don't want to get forced to make a bad move because we have no other options. So if a player has more possible moves to make than their opponent, then that's a good thing. Not all cells are created equal. Some are better than others. The most valuable spaces are on the edges, and most importantly, the corners. These spaces are much more difficult to take, and they allow control of the whole board, since you can sandwich pieces in the middle with pieces on the edges. Corners in particular can't be captured at all once they're taken for the first time, which makes them the best spots on the board. But not only are some cells better than others, some are bad to the point where you want to avoid taking them at all. Most notably, the 3 cells surrounding the corner. If you take one of these cells, it's usually very easy for the opponent to use that disc to take the corner for themselves. We can keep track of how good each cell is for stability by using a matrix of score values. Each occupied cell will have its matching score from this matrix added so that the stable cells are prioritized. Frontier disks are disks that have empty spaces next to them. These are more likely to get flipped, and we want to avoid them when possible. Our AI is already pretty fast thanks to our use of bitboards in C++, but another way to make it faster is to use a transposition table. Imagine a scenario where our Minimax algorithm generates a certain board and evaluates it. Then, during a separate Minimax call, we reach the same board. Well, instead of digging down and evaluating everything again, we should be able to retrieve that previous evaluation and save ourselves some time. The table itself is pretty easy. It's basically just a lookup table. The hard part is how do we specify what evaluation to retrieve? A given board state consists of 129 bits of data. How can we, given this data, know exactly where to look in this table to find what we need? Zobrist hashing is something that is relatively simple in theory, but is difficult to understand due to the confusing language used by sites like Wikipedia. Zobrist hashing hinges on a certain operation called the exclusive OR, or XOR. This operation has a few traits that the other bitwise operations do not. For one, if you XOR the same number twice, it will undo itself. Kinda like if you multiply by -1 twice, then you end up with your original number. The real beauty of this is that it will still work even if you XOR several numbers together. So if I have this binary number right here, and I XOR it by a bunch of different numbers, if I repeat those same XOR operations again in any order, I'll get my original number back. So let's keep an array of 129 completely random numbers. This is 64 numbers for black, 64 numbers for white, and 1 number for which player's turn it is. So when we want to represent a board state as a single number, we can go through every cell on this board and XOR with the appropriate number if it's white, black, or empty. This will result in a mostly unique number that can be used to index our transposition table, and when we make another move, we just need to XOR the new move onto our current hash. I didn't take any exact benchmarks, but using the transposition table should increase our speed greatly. With this, we're basically done with our AI implementation. The results of my efforts are somewhat difficult to determine because I'm not very good at Othello, but the AI is pretty good as far as I'm concerned. I get beaten the majority of the time, though I have managed to sneak in a win once or twice. I also sent the program over to my brother and a friend in order to see if they could beat it. My brother was unable to beat it. My friend was able to beat it, but only by taking advantage of the fact that my AI was deterministic and would always give the same output from the same input. There's basically only two ways to make the AI better: to improve the evaluation function or to make the program run faster. Tinkering with the evaluation function is the easiest of the two, but the problem is it's very difficult to tell if the change you just made was positive or negative. Is it smart or dumb to change this 2 into a 3? The only way to tell is to do it and then play a bunch of games and see if you can tell the difference. So I'm happy with leaving it like this for now. I promise that I'm stopping here because I'm satisfied with where the product ended up, and not because I'm absolutely sick of using C++.